solving this classic Crackme problem. Here we can download a file. I have already downloaded the file in my Linux virtual machine. After downloading the file, we can see that there is a flag section. This flag is being compared with the modified user input. So what we can do is run the code through a debugger. I have already run it with my GDB.jf debugger, and after running with this debugger, what we have done is we have set up a breakpoint at the memory compare function, as we can see in our original source code or the decompiled C code, that there is a mem compare function used. So after setting up a breakpoint in the memory compare function, what we can do is we can move through several steps using the si command or step into command. After moving through the step into command several times, we can actually gain two strings. So one of these strings have to be the flag. So we can verify which one of them is the flag by having a look at our code browser or our Ghidra. Okay, so let me see this. Okay, so if we hover over this, we can see that there is a weird string. But what is interesting, that as we know that this string is stored in the Little Indian order or the reverse order, which we can verify using a simple file command, file Crackme0x100, and we can see that there is the LSB, least significant byte. So this is the Little Indian order. So what we can do is we can actually read LXPYRP, and if we look at this string, it is also LXPYRP. So it looks like the same string as our flag here. Oh, this is not this one, this. We can also have a look at the last segment of the string, and we can see WAJ, or in the reverse order JAW, and we can also see this JAW. So we have successfully verified that this is the flag we are talking about. So I have actually reverse engineered this code, and what I have done is written a Python script to perform decryption and retrieve the original flag. So I can show my script. Here I have simply just written P7 and P6. As we know, they are not dependent on the user input, they are simply dependent on some preset values or predefined values. So we have rewritten as they are. We didn't bother with them. So what we did next, that we have to actually work from the backwards, since we are performing a decryption. But before I do, I have to rewrite this logic because it looks kind of weird. So we can actually rewrite this logic in this way. As we know, if we divide a number by 26 and multiply it by 26, and then if we subtract the result from the original number, we actually end up modding the number by 26. We can actually prove it mathematically. So this logic can be rewritten as this logic. So that's what we have done here in this portion of code. We have actually transferred the P8 on this side, and we have tried to find out the ivar1 here. So here's the catchy part, that they have actually modded the ivar1 by 26. The reason they have modded it by 26 is to ensure that ivar1, which is actually a character ASCII value, they have ensured that they stay within the alphabetic range. So in order to ensure that this ivar1 stays within the alphabetic range, they have modded it by 26. It is not actually an ASCII character per se, but they actually represent the alphabetic characters like A, B, C. A for 1, B for B means 2, or A means 0, B means 1, something like that. So in order to ensure that it actually happens, they have modded it by 26. So in the decryption code we have to also make sure that this ivar1 actually stays within this range of alphabetic character, because if it overflows beyond the 26 boundary, it will actually generate an weird or undefined behavior in the code. So we have to make sure that it is within the range. Then what we have done is we have rewritten this logic. So this portion of the code, it is actually rewritten as it is actually named with P, and this portion of code is named A. So after doing so, we have transferred these portions to the left hand side. Here we have transferred A and B to the left hand side with ivar1. Afterwards we have modded the whole thing by 26 to make sure that they stay within the alphabetic range. And afterwards we have added V8 to the result, because in the initial encryption code we had to subtract V8 from the total result, and since we are decrypting now, we had to add V8 to the result. And after adding V8, we have simply used CHR to generate the plaintext. So after putting the ciphertext from this GDB debugger, we can actually run this script and gain this flag. It is actually not the flag, but this is the original password, which will be later modified to this flag. And when this flag is compared using the memory compare function, we can successfully gain our picocpf flag. So we can actually copy it and then we can run it using /crackme100. So as you can see, we can see the sample flag, but this is the sample flag. We have to run it using a netcat to gain the original flag.